speaker for this session is Michael Klas, who is a recent graduate from the School of Mechanical Engineering, here to talk about bioengineering, biomining of asteroids. Thank you, Michael.
Okay, thanks Naomi. My name is Michael Klas. My project was also asteroid mining based, but we decided to go a little bit crazier than that and went with the microbiology side of it. So biomining and biomethanation processes. We worked with Archaea. We worked with Archaea and UNSW Mechanical Engineering, as well as the School of Babs. So biological resource extraction methods on asteroids can be really divided into two sections: biomethanation, which is biological methane production using microbes, and biomining, which is, in layman's terms, a sort of way of using microbes to either dilute the metal that you're after into an aqueous solution and siphoning it out, or by pretty much dissolving everything around it and then grabbing the metal that you're after. This is the paper that we published a couple of months ago. Naomi was a co-author, and so was Andrew. Okay. And yeah, a couple of other people. If anyone's interested in that, give me a shout. I'll send it on to you. Okay, so why microbial methods? Biomining mining equipment by itself is pretty heavy, and obviously with space biomining kind of methods, you won't be needing any heavy drills or anything like that. It's a very small mass sort of system, so you're looking for a bag type system that will encase an asteroid, so you can induce an atmosphere within this area, and then be able to deploy the microbes to conduct your biomethanation or biomining processes. Microbes themselves, so I'm actually talking about the microbes of the system itself, are very robust. They are known to survive some of the most extreme Earth environments out there: Antarctica, thermal vents in the deep ocean, etc. This isn't necessarily a positive thing, but as we are talking about asteroid capture and space missions, large time frames in terms of methane production or biomining is actually, I mean, it is a long process, so I mean, we've got long missions, so it sort of works hand in hand. This is a bit of a background on sort of multicellular organisms and unicellular organisms. Up here we have the eukaryotes, which is plants, animals, us, pizza. Archaea and bacteria is basically unicellular organisms. Methanogens, which are used in the end process of the biomethanation process, fermentation process, sorry, fall under Archaea. And bacteria are used in the initial stages of the biomethanation process and are used throughout the biomining process. Mission and motivation, basically the NASA asteroid capture and return mission was our main motivation for this, and so we'd want to capture an asteroid, induce an artificial localized atmosphere. So this could either be done by, this could most probably be done by literally bagging the asteroid. Then we would deploy our microbes. They would use the chondrite or the regolith on the asteroid to conduct the various processes. You'd want to get into mineral and fuel extraction afterwards. So if you're producing methane in a bubble, you'd want to siphon that off before it sort of explodes. Yeah, so obviously that's siphoning it out, external storage sort of thing, and then the delivery to the end user. We sort of envisage a delivery to the end user being the local, like, sort of satellite market initially. for both repair and refueling missions. Asteroid composition, this is very basic. We've got silicate, carbonaceous and metallic asteroids. For biomethanation, we need carbonaceous asteroids, which have a lot of water on them as well, so that is pretty handy. And for biomining, obviously we need metallic asteroids. These are some of the governing factors that we need to control for any process. So we do need to be able to ensure there's enough nutrients available on these asteroids. We need to be able to control the salinity of the process, and the pH control is also a massive factor, as biomining, for example, is a very acidic process and biomethanation is very pH neutral. The physical structure of the asteroid basically refers to the composition, the physical structure, which means if it's a single rock, or if it's porous, or if it's made out of rubble. Basically, the more cavities and the more porous the asteroid is, the better the biomining or biomethanation process would actually work. You've got a lot more surface area to cover with these tiny little bugs. I say water accessibility, not availability. We know there's water available on carbonaceous asteroids. It's just not going to be accessible unless it's going to be heated up enough to get liquid. So these are some of the space environmental parameters that we need to negate. Heat. So for both the biomining and the biomethanation process, we're talking temperature ranges between, and this is very extreme, -20 and about 80 degrees. So yeah. Usually we're looking at about 20 to 40 degrees for these processes. Over here we have a little bit of a depiction of the microgravity and 1G gravity environment in terms of nutrient availability for microbes. You can see here the nutrient availability is a lot more in the microgravity environment than it is in the 1G environment. However, afterwards you will only have limited amounts of nutrients left in this environment. In terms of radiation, we need to protect these bugs from the harmful radiation out there, and be that in a near-Earth scenario or in deep space. The vacuum, low-pressure environment, this is actually part of the experimentation that we did that I won't be able to cover in this, but we sort of found out that if you expose bugs to low pressure, they sometimes actually produce more than the ones that haven't been. So in terms of methane production, that was pretty cool. Other factors, methane propulsion is in essence, could potentially be a more efficient propulsion system than conventional hydrocarbon fuel systems, mainly due to the complexity of the system, as the methane and the oxygen as the oxidizer have a very similar boiling temperature, and hydrogen and oxygen, they're pretty far apart. Minerals and metals, basically, with biomining we can get copper, gold, iron, cobalt, nickel, etc. And all of these metals are available on asteroids, so that correlates quite nicely. In terms of legal and ethical concerns, we've heard about ethical concerns yesterday and the legal concerns as well. And putting bugs on asteroids is probably just another addition to everything. In terms of the economy and commerce, here's a picture of every single satellite in orbit around Earth. It's a very used picture, but basically we've got about 3,600 satellites in Earth orbit, of which 1,000 work. The rest don't actually have fuel or aren't capable of keeping on with their mission. We've got 400 of these, which are geosynchronous telecommunication type satellites, and in terms of a case for economy, if you supplied one of these satellites with enough fuel for a single year for station keeping, you could basically ensure about $18 million worth of revenue for that company per year. In terms of the design concept, this is from Planetary Resources, and our system would sort of look very similar to this. We would find an asteroid, we would bag it, ensnare it, make sure that it's tight, because otherwise you'd have a lot of like methane going out, basically. In terms of the bagging system, you need to ensure that an environment control and life support system actually ensures the survival of microbes. And that's in terms of nutrient availability, etc., etc. And the resource extraction process in terms of methane production, making sure that there's not an overpressure within the system. And then possibly also ensure that there's storage and a refining process attached to this. Another nifty thing that we found was from Deep Space Industries. It was just an article that I found once on a gel type solution where they would use a gel instead of a bag to basically put on an asteroid, and that would seep in and basically start this biomining process. So that's pretty cool. In terms of future work and conclusions, potentially yes, this is quite feasible, especially because a lot of asteroids out there are very porous and rubbly. So a single rock isn't really going to be the most useful thing for us, whereas the porous and rubbly asteroids are. This future work is based on mainly my thesis experimentation work. So we want to be testing a large variety of strains and different types of strains, different consortia put together. Test combined effect analysis, so you'd be testing microgravity environment, low pressure environment, heat, radiation, and potentially even like put all of these together into a single thing. When I say ecological theory testing, there's two theories out there, ecological theories that would support this, and this is niche construction and island biogeography. If you want to know more about these, it takes quite a while to explain, so I'll explain it later. But yeah, basically we could fill a vital niche in terms of in situ resource utilization capabilities, and yeah, thank you very much. And yeah, this is the team that I was working with, and a lot of awesome people there. Thank you.
Thank you, Michael. Any questions?
Just to verify,
Yep.
you got methane-producing bacteria,
Yep.
put them in a vacuum,
Yep.
and they went, yum, this is great, we keep working.
Okay, we put them in a vacuum, then took them out, and then they actually produced, some of them produced more methane afterwards than the control samples.
Okay, so they temporarily live in vacuum.
In a way, you could sort of explain it in terms of pruning a bush. You basically prune a bush, and then it starts growing better. Yeah. Does that make sense?
Yeah.
Sweet.
Questions?
Oh, sorry.
That's all right. My question, when you were talking about other metals,
Yeah.
other things that you can extract, can you talk a little bit about what you get? What do the bacteria do to break down the material you want to remove and leave the material you want? How does it work?
So in terms of the biomining process
Yeah.
itself, okay.
So it's not a gas, I guess, like now here
No,
gas
no,
coming out.
so personally my stuff was mainly based on biomethanation. So from what I know in terms of biomining, because it is quite related to this, that's why I presented both of them. You have the two strains of biomining, the bioleaching, biooxidation I think they're called, and one of them would allow you to have a heat. So basically it's all the stuff that's left over from your mining trails basically, and then you have the water, you put these microbes into an aqueous solution and you sort of dilute the metal out. And in terms of an asteroid, I don't know how effective that would be with a microgravity environment, but yeah, it is an option. Yeah. Does that sort of answer?
Yeah.
So do you have an estimate of how long this process will take to?
Years to decades. Yeah. So it's a pretty long thing. yeah. Anyone else? Sweet.
Thank you, Michael. All right, I'd like to just finish off by thanking all of our students. They're just the representatives of all our many students who are doing wonderful projects. And thank you for being here. And yeah, I think we have a break now. Yeah. Thank you.